I'm Troy Tittlemeyer, CEO of MagmaChem Research Institute, which we will get into a timeline and just in general. And across the table is Stan Keith, and we will have an introduction to MagmaChem, the history of MagmaChem. We'll get into that in a minute. Now, executive decision, Stan. Do you want to do a tutorial of our website as it's the new functionality, kind of show them how to get to the publications, how to get to the future courses?
Right
now, or you want to do it at the end?
No, let's do it now.
Oh, okay.
He's melting down.
Slippery fingers. Okay, this is the new revamped website. We have what Stan calls the Angry Earth model. This is a dynamic layered Earth model. This is a core model tied to tomography and tied to the Magma Metal series that Stan and MagmaChem have been developing since the 80s, which we'll get into. Stan working his magic on the outcrop. There's Monty breaking rocks and giving them to Stan. Cracks of the world. We talk about that one all the time. That's actually our friend Martin Hovland and Stan. What is that? Green. What did you?
That's at the new Adria here.
Oh, new Adria. Okay. Looking at some serpentinite.
Serpentinite.
And some of these graphics we just wanted to put there as images we can cycle through at the top of this website. Serpentinite is the unique story of MagmaChem, one of the unique stories. Of
That's Chiboa in Brazil.
This is Stan earning
a gold play for Anglo Gold.
Right, earning your respect with the.
Oh, it impressed them. They had nothing for me until I picked that snake up.
But we are a nonprofit, and that's very, very important. And that's because we have a PhD, Dr. Jan Rasmussen and Monty and Stan. We have this technical team, so we're teaching, and that allows us to qualify for a research institute. This is just a little bit about us. This is another tutorial outside of me doing this. This is how you get in. Boom, become a member of MagmaChem. Join this community so we can talk through all these things. We have a Twitter. We have a Twitter account. Monty, he's messing with that and keeping that going on the social media side. Let's go publications first, and let's go there. Publications. You have membership publications and you have MagmaChem publications. Membership publications comes with your membership, yearly membership. We have over 100 articles right now. We're probably at like 50, but they're coming. And so you have full access to what's going on here and through the years of MagmaChem, and it's basically Amazon for MagmaChem, as we try to make it that simple. They don't individually cost anything. It's when you become a member, you get access to that. However, MagmaChem has a ton of things that have not been published, and we're working really hard to publish. And this is one of them that is officially a MagmaChem publication. And this is important because you got to read this one, just like I'm reading it. Everybody that I know is reading it. You got to understand the Magma Metal series approach, basically, to really get the most value out of our course, which is the UDH course. It's the integration of the mantle and the crust and the processes that made that happen through geologic time. If you don't understand this one, yeah, you'll get a lot from everything we're talking about, but you got to get the whole thing. We have 13 weeks. This is one, and we're going to get there. I promise. We've already worked well ahead of time on a lot of these. It's been amazing. So this is where it's going to be. You can come here tomorrow or by this weekend. We'll have the video from the class of Stan and MagmaChem presenting what we're presenting. You'll also have a copy of the presentation for a minimum donation to MagmaChem Research Institute. The introduction, you obviously guys are all here, and you get the introduction that we're doing today. So we got a long list to get to. The introduction is here. We're going to do geology shop. We're going to bring back MagmaChem from the 80s. We're going to have hats and T-shirts and coffee mugs. You can learn more about us at the staff, and as always, and everybody that knows Stan and Monty, you can reach out anytime, and we would love to share ideas and attack problems that we're all messing around with. So that's a tutorial of that. And without further ado, Mounty, please walk us through a parallel timeline of MagmaChem and geology.
Yeah, this is a history of MagmaChem put on a timeline leading up to the UDH model, the Ultra-Deep Hydrothermal model. So it started back in the 70s with Stan and I at the University of Arizona. And together we have degrees in philosophy, engineering, and geology. And there's this great quote that we just love. It's geology, and in general science, has become islands of conformity surrounded by interdisciplinary oceans of ignorance. And we took these three disciplines and we sailed the oceans between them. And that's kind of the beginnings of Magma Chem. But it even goes back way earlier than that, when there was a boy in northern Wisconsin born in a blizzard, and a little later a boy was born on Christmas morning in California. That was Stan and I. And we both had neighbors that hid minerals and rocks and fossils for us to find. They were mineralogists, actually. And that got us started. And what the point I'm trying to make is that we started with our boots on the ground. And Magma Chem started that. The patterns that we eventually have looked at started there. So mapping is the very beginning. And then if you look at this timeline in general, you've got mantle, crust, and then serpentosphere. You can kind of divide it into three parts. And the mantle began, in the 70s. Stan will get into exactly when that happened. We founded Magma Chem in 1983, worked on the mantle, and it's really the source. And then we got into the crust and the processes in the crust. There's this debate that's been going on. My phone rang. John Mark Stouty. I wonder if I should answer this. John? John Mark?
Really answered it. All
Trying
right,
to
we're
get
gonna.
on. Why don't you call Troy? He's one of the
He got
co-founders.
special treatment.
He's allowed to make those kinds of interruptions. All right, the password has been sent.
Anyway, okay. So let's see. What else should I talk about here?
Well, we're getting out of the mantle-focused geology, petrology, and everything that Magma Chem was doing, and then we're obviously getting into the crust, and that integration between the two is amazing. That's part of the big story.
Yeah, there's really a debate been going on for about 500 years between Descartes and Agricola. Descartes was source, and Agricola was lateral leach, getting metals out of the crust. And I think Magma Chem has solved that debate, because what the mantle does and what the source does is in our science. And then the Serpentosphere, I think what started that, besides low metal prices, and we started looking at the oil and gas industry, gave a paper at an AAPG conference, and Exxon Research came up to me after the paper and said, when we do the accounting for supergiant oil and gas accumulations, the books don't balance. You have any idea what we're missing? And it's a long story, but eventually we discovered this process of serpentinization, which has been overlooked actually since the Penrose Conference in 1968, when they rejected Harry Hess's idea that there was serpentinite down in the Moho. Anyway, so we eventually came up with this idea of the Serpentosphere,
Right.
another sphere on planet Earth, and then we got together with the Norwegians, and the Ultra-Deep Hydrothermal model started evolving. It's a window of time from kind of analog, when we were in the field and we did things by hand, and now we're in this digital age, and there's this kind of this window between those two times when a lot of technologies were developing, like age date technologies and analytical chemistry, computers, geophysics, GIS, satellite imagery. And without that, it would have been very difficult for us to synthesize and integrate as much data as we have been able to do. So it's been a very special time from the 70s until, about
This
the early 2000s.
Well, to today, Monty, you're talking about a transition in a window of time right now that allows us to take this goofy equipment that Stan absolutely hates, but it allows us to talk about this. It allows us to put this out, and it allows us to back it up with a long presentation that everybody can watch on their own time and take their own way. That wasn't possible before. And so this information is being delivered fast as possible and as accurate as possible. And it's at this window of time right now before everything gets a little too out of control, maybe. Monty, if you're done, we're going to jump to Stan. Stan is going to say a little bit about his take on this parallel timeline, and then we're going to move on.
Yeah, while I was watching this, I had a micro epiphany. You see the thing up here called hard rock and soft rock. Okay, so we came up through the hard rock school, actually hard knocks school of the University of Arizona. And then around 2000, we graduated into what ultimately is the soft rock school. And of course, that's oil, petroleum geology, et cetera, in the conventional sense. But really what has happened here over the last 20 years, 30 years, is we've integrated hard rock and soft rock. And hard rock essentially is what you'll see that we developed is called the Magma metal series classification and all of them. And that was pretty much together by 1991. The identification of the Serpentosphere, which is the Earth's moho layer, and the idea that that is, especially in the oceanic basins, is serpentine group rock, came in 2007 when we were on our way to Norway in a business lounge of Northwest Airlines. But that ultimately traded on one of the Norwegians, who I don't know whether he showed up yet or not, Martin Hovland, who coined what we were doing at the time as UDH, which was ultra-deep hydrocarbon, but linked to serpentinization. But serpentinization is not serpentine is not ultimately a hard rock. It's a soft rock. And it is the source of all of the soft rock hydrothermalism that leads to oil, saline deposits, black shales. Maybe 70% of the rock on the sedimentary rock record may have something to do with the serpentinization process and may arrive in high density brines from the deep. So that's what led us in here. So it turns out the soft rock story is bigger than the hard rock story.
Let's take it, but let's rock it back to 1978. Let's go to the next slide.
Oh, okay. So
this is Stan holding.
Yeah, the Geology magazine. And that's what that cartoon made the cover. You see the cover go up into the right there. And yep. It wouldn't have been possible, nor would this meeting today have been possible without this guy, who unfortunately is now dead. His name's obviously Bill Dickinson. And he saved that article. It was under a lot of peer review fire at the time, specifically from one of the guys who was the president of GSA, and he didn't like it, so he told his editor to can it. And then after a whole bunch of stuff, which I don't need to go into, this Bill wrote a letter, and all of a sudden it completely turned everything around. I had no idea that this was going down. But I really want to give a shout out to Dr. William R. Dickinson, great geologist, mentor, ultimately met him when he came to Tucson. Actually, I had something to do with getting him to Tucson. Just a great guy. And unfortunately, he's moved on. Okay, so. That
paper, though, in a sense, and that graduate degree and getting through that when you were pretty much out of money, out of time, you were done with school. Officially, you had an amazing thesis, enough for Dickinson to do what he did and push this thing forward. But what came right after that was very interesting to me. And that's, you had the opportunity to, for 3 options as a professional out of graduate school. You could have went consulting, industry, or academia. You had those 3, and state geologist. You chose the state geologist route right away, but you always kept true along this whole story as a consultant, and you never took those really crazy salaries and the opportunity to go with a big school or go with a big operator. That's really important to me.
Well, yeah, that gets at the idea that everything that Magma Chem has done has been integrated with the overall Magma Metal Series Serpentosphere concept at the end of the day, although the Serpentosphere didn't show up on this one. But here you can see the beginning of the layered earth concept, where I took a modified Peacock petrological classification and tied it into depth to a subduction zone, which comes from Bill Dickinson's and Trevor Hatherton's potassium depth correlation. But I integrated it to petrochemistry, and that hadn't really been done before, other than they had linked it into potassium and depth, but not the ultimately whole rock. And then when I was doing this, I noticed that certain kinds of mineral deposits, like copper deposits, tied into that Ca thing. The AC thing was tied into lead zinc things and silver things, and on and on and on. And that ultimately led to the Magma Metal Series mega chart. Let's go to the next slide, which was initially put together at the behest of Ray Morley, coming out of a short course in Salt Lake. Says, I'll pay you to do this because I want some kind of visual for my guys. And Monty is trying to blame Gary Heinemeyer for this. He may or may not have something to do with it. I'll have to get Gary's version of it. But anyway, that was an early take on what Magma Metal Series was.
Sorry for the
and
quality.
At the time,
of
it was called Magma Series. The key thing about this, as it evolved later on into this 2007 version, which is still the current version, is that magmas are the source of metals. So it's a source-based classification based on descriptive petrochemistry and mineralogy. And the other link is an empirical link to the metal contents and compositions of the associated time and space mineral deposits. So that all got folded into here. Now, that then developed into what ultimately is a layered earth model, because I took the Dickinson Hatherton KH classification, and after we had all of these things sort of put together empirically, I said, let's do a fun little exercise and let's see what the potassium depth thing is for the layers between these boundaries. And so that's this little chart here, which you can read at your leisure. And then we said, well, let's see, somewhere I've seen something similar to that. Oh yeah, maybe let's go into the geophysical literature. Bingo. This was what was in the geophysical literature at the time. And the matchup between the geophysical layering and the seismic data and the geochemical model was striking.
Yeah.
And so all of a sudden, that was a huge epiphany. And
you said you're on a high for about 10 years off of that.
Well, I'm still on a high.
Yeah, you got isotopic data with this.
Yeah, over here is the isotopic data.
You know,
over
how
here is the metal contents of the mineral deposits. There's a lot of stuff on this thing, which you can read at your leisure.
I don't want to get into a rabbit hole. If it's a quick answer, because while you were talking, I was thinking, you know how you can predict what was happening or what the implied tectonics are under an oil field based on type 1 versus type 2?
Yeah.
How does that kind of concept correlate to the metals side of the business?
Well, as it turns out, yeah. This pink layer, which is our quartz alkaline layer, there's a lot of oil deposits that initially start with periddotites that come in and start in that layer. Mm-hmm. And that's the Kupferschiefers of the worlds. And then the guys from this layer are ultimately, you have things like gold deposits. We now think that the homestake type gold deposits are magnesium/calcic layer sourced.
If you're seeing that stuff, you're in flat subduction.
Yeah, in terms of tectonic setting, usually these are best maximized in a flat subduction scenario, and these are you see in steeper subduction scenarios.
Wow. Okay, sorry, that was cool. Okay, so at the end of the day, Stan, what was cool, and it's something that Monty just brought up, the movie Moneyball, and how they came out with this new algorithm to pick baseball players and make World Series championships, and everyone said, not going to work. You're out to lunch. Get over it. And then with time, it proved to be successful. And so the same thing in a similar way happened to you guys with the geologic community. And with time, you guys have contributed an unbelievable amount of actual resources.
Especially on the metal side. We
Right.
ultimately developed this model into a very specific, predictive, target-oriented model at the drill hole scale. And that led to and contributed to the discovery of all of these things.
Each one of
And there's
these can
actually
be
more of
found.
them.
We'll have the success list on the website, right? We'll have that available
Yeah.
in the publications.
Yeah,
You
if
can
you
go
want to
through.
get into the gory details of that.
Well, the coolest part to me, and I think to everybody watching, is that how did you actually start breaking down the data? And in that success list, which is a very long document, you actually take the time to explain. In 1984, you received the geophysics data, then you received structure maps, then or whatever it was, and you started just chipping away and putting it ultimately into the geochemical vector.
Yeah, and
thing.
all of these at the end of the day were rolled into the global database and just added into the whole Magma metal series concept.
Right.
So these were all tests
Right.
of that mega chart.
And by not
At a
taking
more specific
employment
level.
from anybody, you stayed as a consultant. You said, I'll give you 2 years with this data, then it's mine.
Well, we
something like
did
that.
this on a consulting basis.
Right.
And that was a very deliberate piece of the business model because I didn't want to work for an Exxon where Exxon gets what you do and says, see you later. And you never get to use that data again. Now, I did make a few deals with the devil, including Exxon. They got all of my
Easy,
hard
Stan.
copies of the time slice maps we did of the Western U.S.
And it's in a salt mine somewhere.
Yeah.
Where is this mine?
I think it's in Oklahoma. But maybe somebody out in that audience knows where the Exxon salt
We
mine
need to
is.
get in that thing. But that's just to kind of button up a reality of how this model actually makes predictions that are real. You predict that this drill hole is going to hit something, and it does, and it becomes real. And that's, at the end of the day, the model
Sometimes
is.
it doesn't. But
Sometimes, of course.
But our success rate is a lot higher than the typical success rate.
And just like the saying goes, you get a dry hole. Well, you probably learn more from those dry holes than you did from the ones you actually hit. So it all goes into.
Well, everything's a learning experience.
Right. Now, this is Miss Jan, Dr. Rasmussen. Gosh, Jan, I'm sorry. She's the whole reason why we have publications for you guys to have at your fingertips. She did a crazy amount of work on the back end, allowing us to integrate it into this website. It's a relational database. So when you type in Serpentosphere, it pops up Serpentosphere papers and publications. And it's really, really good. And that's because she's been an amazing part of this wheel since when? What did she say?
1978 is when we first really started to get going together on a collegial basis.
The land of Cochise.
Where we put together these road logs, which are still well used. That's when she started to become quite intrigued with the whole, what would become the Magma Metal Series thing. And in the early 90s, late 80s, she came up to Seattle. That's where I was at the time. And rifled through my database and put this neural network study together, which is basically a PhD in magma chem that she got at the University of Arizona.
Incredible story in itself.
Yeah, I don't want to. I was going to be on the committee, but I won't go into that story. But
the coolest part is, man, I mean, machine learning and algorithm and all that kind of stuff, neural nets. I mean, she did it.
Well, the computer did it at a fairly primitive level, frankly, but nevertheless.
Not as powerful as Stan's brain.
Well, Stan's brain is always out trying to figure out something else like we just did a few minutes ago.
Right. Okay.
And then we also worked together on the Yucca Mountain, which we did a lot of work in Nevada to typing all the mineral systems, and we published that. And that actually did catch a piece of UDH as related to oil deposits in Nevada, Railroad Valley type ones,
Right.
of which the two Norwegians are aware that we have one over in Snake Valley in Utah that's still waiting to be looked at. That's one of the ones that's in our queue to be discovered.
Right. Okay. Let's let Monty explain and talk about his history with you through the time, and then we'll move into the actual, technical presentation shortly after that. Monty.
Well, it started in grad school at University of Arizona. We were in a volcanogenic massive sulfide seminar, and there was this tall guy with a beard. He stands up at all the graduate students, all the professors there, and we're just puzzling over this mystery of volcanogenic massive sulfides. And he just, every once in a while, he'd say something, and I said, this guy thinks differently than anybody I've ever seen. And I think it really has to do with, he calls it anomalies. He sees anomalies and he puts the anomalies together. I call it pattern recognition. He recognizes a pattern between anomalies. And he was doing that during that seminar, and I had to meet him. So I met him and dragged him out to my thesis area, which was Stockton Pass, looking at some shear zone and Precambrian rocks that was a big mystery. And actually, this picture here is Stan and I at that time kind of overlooking my thesis area. And it's so prophetic. We're looking into this fog. We had no idea what would happen 40 years later. And on the right here is us, 40 years later. 40,
Right.
I believe it's 40 years. But I think, this thing about pattern recognition, Stan can get more into how he thinks of it. I was just reading his little essay on the lost art of geologic mapping. And he's, Stan is a master at geologic mapping. I'm not too bad either. We both were kind of stars in our field camps. So we started, as I said before, with our boots on the ground. It all goes down to geologic mapping. But that essay he wrote is, it's creative writing. He gets so passionate about it and so poetic. It's really a neat thing. We'll have to post that article for you guys to read, because I was going to read some excerpts, but I think Stan would go, "Come on, Monty. You're just getting a little bit too warm and fuzzy here." But
Right.
beautiful.
He's scoffing on this side. Yeah.
Beautiful language in that, but that it really boils down to that. That's where our roots are on the rocks, and that's what we're doing. Is we're reading a story written in the rocks. And
so you were kind of a field extension. Obviously, you're a credible mapper, a credible geoscientist. Your structural analysis of anything we've ever talked about is always just fascinating to me. Obviously, you're at a very high level as a geoscientist, but in relationship with Stan and relative to Stan, was that kind of the teamwork throughout the years? It was like, I got to be over here. Monty, I need you in Mexico for 7 years, breaking rocks, collecting data.
That's right.
Not exactly.
This is such a long story. It's hard to get into the details right now, but to think that we've been together this long, we have to live 1,000 miles apart. Burn each other out.
Right.
Oh, they're absolutely yin and yang. I'm blown away to complete opposites in every way you can imagine.
Yes.
Complete opposites,
except for the story we're reading in the rocks. And
geology somehow is able to keep you guys together, and your brothers 1,000 miles apart.
Yeah, it's this Magma Chem approach is the big pattern. It's the threads that hold everything together.
Yeah.
That's what we want to share with you guys.
Yeah. Okay. Dan comes into the story pretty early in the 80s, right?
Yeah.
So, Monty, you want to say something just real quick about Dan? We won't read this. It's just for people to have. This is part of the presentation.
Yeah, Dan has got extraordinary talent in the library, in compilation, putting things together. He's been just a solid foundation for Stan and I over the years. He's been working with us since 1985, I think. I think that's when
84.
84. It's he's a very close friend, and he kind of lives sort of halfway between us.
Yeah, he's great. He's great. Okay, and then there's me, and all I got to say is I don't hold a candle to anything in this operation. I sold everything. My wife and family was in support of this idea that there is a message that's coming out of Sonoyta, Arizona. And if I plant myself there and dedicate the rest of my life to this, I think something really, really cool can actually happen. And so I did it. Here I am. And this is 1 year since we did that. Me and my wife and a brand new baby and a baby on the way. I met Monty, I met Stan, and I mean, this is standing on the back of Monty's property in Evergreen, Colorado. And you know, that's kind of a random picture, and it might have some other things going on. But more importantly is I sat there and I questioned. I was dazed with him, questioning and looking at the data. And Monty has an incredible way of explaining and articulating good enough to really understand the broad context. And then I meet Stan, and he's going, broad context, I mean, get into the gory details. And now I have reached my intellectual limits daily with Stan trying to break this up. But Monty took me out to this outcrop in Denver, clearly an injectite that was popping just straight through Precambrian rock. And I remember standing there, I grab a rock, he goes, look at that. And I put my hand lens up, he goes, who taught you how to hold a hand lens? Hold it like this. And I'm going, wow, Monty's he's just the real deal, is my opinion. And then we did a field trip out in the Franklin Mountains, and that's when I realized getting Stan and Monty together in the Franklins, which is that picture that Monty was talking about on his slide. That's when I went, there is definitely a totally different interpretation to the basin that I've been studying for the past 5 years. What is this? And I want to know. Stan, it's an honor to be here daily with you, and for the opportunity that you gave me. Let's go. All right.
Okay, so what we're doing right now is sort of writing a book on, and it's going to come out as a series of webinars, and then those will get punched into a full-blown manuscript. And it ultimately is the story of the UDH component of the classification applied to the origin of oil. And the origin of oil it starts with, and it doesn't quite end with, there's a few other things you could see here along that it's related to all of those things, that turn out to, from the Magma Metals series UDH perspective, to be highly anomalous with respect to the conventional wisdoms about oil occurrence and formation. And I might say that just about every subject, in like even porphyry coppers, et cetera, there are anomalies in all of those in terms of what you'll read in the standard science journals that these things explain, that the UDH and the Magma Metal series explains.
And we kind of thought about how we're going to do this introduction quite a bit. And it was the idea at the end of the day that let's line up the 35 anomalies, problems, issues, whatever you want to call that UDH provides solutions for. Whatever you want to call it, let's go one by one, a high level, because we got 12 more weeks of this that are actually going into the details of where Stan and Monty grab that data from the publication or whatever, what the whole thing is put together in detail over the next 12 weeks. We're going to go one by one by all these very interesting anomalies in the data that for most of us, we shelf and say, that's an anomaly. It doesn't help me in my prediction. And that's because the model's it can't take it, but the UDH can. So this is us going for it.
Okay, so we
Oh, you want to say more?
To that. So basically, you can break it down into a series of 7 anomaly categories. Most of them, the big one is Kerogen anomalies. Then there's all these high energy mineral and rock anomalies, and by that I mean minerals and rocks that don't normally associate with the normal oil window, which is 80 to about 135 degrees C. A lot of these minerals occur way above that, and they're saying they're saying there's something very anomalous as to what's going on with the hydrocarbons that are associated with them. And then there's the black shale problem, which even conventional oil wisdoms now realize is not just a source rock, it is now a reservoir rock. And so now all of a sudden that's become unconventional oil, but in fact that's a huge anomaly with respect to their whole model. Selenization and brines are another major issue. They're not just accidental brine waters, or mostly they just look at them as water, and they're not water, they're brines. And it turns out when you look at places like Mars, you'll find that there's a lot of brines on Mars too. So that we'll get back to that in a minute. And the thing that is persistently associated with oil is the notion of mud volcanism. And basically you can find not just a nice little mud volcano hanging around, but you find most of these things are occurring down below the level of the mud volcanism. So you'll see things, really weird things like injectites that are very spectacular geologic features that typically are overlooked by most petroleum geologists. Then there's oil problems, one of them being the experimental data that was generated by Lewin, where he couldn't generate oil until he got over 300 degrees C, which was 2 to 3x the conventional oil window. And that's a whole proof of concept for the hydrothermal oil approach.
Mm-hmm.
And then there's the biosphere. There's not enough dead dinosaurs to go around to make all the oil that we actually see. And that's one of the reasons that Exxon approached us back in the early 2000s, because they recognized the same mass balance. And they said, what's this thing called serpentine? So we went down that rabbit hole, which turned out to be a very good rabbit hole to go down.
Okay, plot twist, Dan. We're going page by page, and we got about 2.5 minutes per page.
This guy is really riding herd on me. But yeah, so we'll just page down through some of the Kerogen anomalies. That's what Kerogen looks like from the North Sea. But more to the point, primordial Kerogen occurs all over the place. And by primordial Kerogen, we mean something that is relatively unhydrogenated. It's mostly a polyaromatic hydrocarbon, or abbreviated PAH. And it's all over the universe. It occurs in meteorites. Turns out big time on Mars now, other microplanets. Very persistent in mantle rocks, in serpentinites, talc. Lots of things that are unconventional to where oil should normally hang out. And thanks to the Norwegians, 2 of which are in the audience, they gave us a lot of rope to hang ourselves on, and we went out and collected a lot of crazy rocks like talc, serpentinites especially, and showed that, yes, there is, in fact, Kerogen as analytical TOC in these things. And that is very anomalous to the conventional model. So there's something else going on here with respect to the origin of oil. Next. Okay, so this has to do with some Martian meteorites. And for those that tuned in, I know Anastasia's out there somewhere. We talked about Martian Kerogen and the potential for hydrogenation of that Kerogen by Martian brines in the context of Martian hydrothermal brines associated with the Gale Crater. And we're reinterpreting Gale Crater as probably the largest mud volcano known in the solar system. It's 96 miles across and 18,000 feet high. I don't know of one that's bigger than that, although there's some pretty big ones in the Caspian and in the Marianas. But anyway, there's Kerogen in it. And the Curiosity has been roving around up there, and it's got a full analytical laboratory on board that is capable of analyzing this stuff with a laser-induced spectrometry instrument. And so that they can do whole rock analyses and all kinds of other things, but including basically what's Kerogen. What is Kerogen? And it's there, and it's getting hydrogenated.
In the research, just for FYI, if you're reading into what's happening on Mars, the scientists that are putting all this data out, they're calling kind of a synonym, I guess, of
MMC. That's called macular molecular hydrocarbon.
right. They're using
Equals kerogen.
right. So those are interchangeable in this discussion. Okay.
Yeah. Okay. Now, the other anomaly about kerogen is that it occurs on this planet, of course, and you can chase it all the way back into the Archean. Here we're looking at the 3.4 to 3.5 GA Strelly Pool Formation. That's a huge anomaly because in terms of conventional plant mass or other biospheric mass, we don't have enough of that until Middle Ordovician time, about 450 million years ago. But here's something that's 3.5 and it's generating. And the other cool thing is they now know that there are serpentinites that are 3.8 billion that have been dated. So basically this goes back, if it's related to serpentinization, and we think it is, all the way back to 3.8. So it's been around since early in Earth history, and it's been generating hydrogenated kerogen. So the oil making process has been around early in Earth history on planets, on meteorites, in places where I think there's oil deposits on Mars, for example. Just a matter of roving around enough to dig them up.
Yeah, we need a big drill, I guess.
And then there's also young kerogen. These are pictures of kerogen from really young Holocene age sediments that are fully matured kerogen, as you can see by the chromatogram there on the left. And Anastasio like this, because supposedly kerogen needs time to mature from a dead plant or a dead animal. This thing, whatever made this, didn't have time at all to mature. And the bottom line is that kerogen is largely made this way. So it's not made, you don't have to have any time. It just comes out this way as part of the process. And the other fun one is this is a hydrothermal quartz crystal, a Herkimer diamond from New York, that has actually picked up some kerogen and has globulated it and is manufacturing it into oil. You're literally looking at the oil formation process that is forming in the context of a quartz crystal. And the fluid inks on these crystals typically are at around 200 degrees C. So again, you're looking at a process in this crystal that's going on well above the oil window. So that's another anomaly that can't be explained by the conventional wisdoms. And then we also see kerogen in the context of elemental metal anomalies, metallic elemental anomalies. Here's a picture of a chalcocite black smoker coming up and teeing out into a horizon just below the highly carbonaceous Kupferschiefer shale, which is a very kerogenous shale. And in fact, in places, it's a shale oil play in other parts of Germany. This is obviously in the copper mines. And this one's actually at Rudna in Poland. But again, it's suggesting a process coming up from a deeper horizon that's not only the source of the copper, but the kerogenous material, which is the chalcocite, by the way, goes right out into that sort of exhalative horizon that's making the Kupferschiefer. So again, another mineral-related process. And here you can see a nice picture of the Kupferschiefer chalcopyrrites that are diffusing out into the black shale as these leaf-like things. The kerogen is the darker material in the matrix, and then the lighter material is clay-rich, probably an oolitic clay or potassium-rich clay. In fact, some of these are full-blown muscovites in terms of 1M muscovites, which are 200 degrees plus. So again, you're dealing with a temperature well above the oil window.
This is happening and diffusing out into the shale as the mud
shale, yeah,
is
all of this
deposited.
is in a soft sediment type context, yeah.
Okay. So if you age dated that shale, then this shortly after.
It has been age dated. It's at about, the illites out of that, the high quality illites out of that are about 252 million, which is exactly at the Permo-Triassic boundary.
All right.
And here's another place where kerogen shouldn't exist. And these are alkane extractions from kerogens that have been retrieved from mantle materials. Now, what we've done is we've borrowed the whole rock data and other off-plot information here and shoehorned them into the layered earth model. And but this just shows the kerogen component of that. One of the cool things is that the deeper you go, the higher the C numbers seem to be. So when you're in the really deep ones, you see the C28. Those are out of lucitite diatremes in Wyoming. And then our definitely normal alkalics are C21 to 24, then C22s maxing out. And then when you get into the more hydrogen-rich guys, C19s for the higher level peridotite. So, but those are all alkanes that are existing in the mantle. Alkane hydrocarbons are supposed to burn off by 130 degrees C. Here we're dealing with 1,500 to 2,000 degrees C. Way down there in the mantle.
Right. Hydrocarbon's very stable. It's one of the main points.
Yeah, there's no deadline for it.
Kerogen, we know for sure, is like really stable. That was told me in undergrad. Like you could put as much heat and whatever you want on kerogen, and that thing will stand. Everything else will be gone. Kerogen standing.
Yeah, but what's interesting about that kerogen is that it has it's almost a hydrocarbon rock that's composed of all of these different hydrocarbon compounds, which include the aliphatic alkane hydrocarbons. So, for example, in that Martian meteorite, that kerogen and its contained aliphatic hydrocarbons survived a crash into the Earth, where you had temperatures probably up at 2,000 degrees C and high pressures, and they just went right through that. So they're incredibly refractory little beasts.
All right, carbon isotope anomaly. What are we talking about here? I'm not good with isotopes. I'm going to throw that out there, Stan.
Well, this is a typical, this is from Fur Green and others, 2004, and then I've added a few other things bolted on here. But basically, we're looking at the C12, C13 ratios, carbon ratios, isotope ratios. And the big takeaway from here is that meteorite kerogen, peridotite xenoliths, oceanic gabbros, lots of other rocks that this was retrieved from carbonaceous material in those rocks, form a window from about minus 31 to about minus 18 or so.
Okay.
Yeah, that window right there. And the big deal is that oil itself, which you go down to the bottom of that diagram, forms in the same window. So all of these are permissively, that oil is permissively related to some kind of source ultimately tied to peridotites and xenoliths, et cetera, et cetera.
Cool.
Okay, so this is just the energy problem, the idea that what we've been sort of skirting around here, where these kerogens that ultimately get hydrogenated into oil, we're now calling them hydrokerogens as opposed to PAH kerogens. And basically, you need water to do that. You need water in high energy environments. Even by the time you get to the subcritical, supercritical boundary, you want to put your cursor on that up in the upper part. Yeah.
Yep.
So we're dealing with a very high energy process. And when we get above that boundary, that's where things ionize and the water starts to react with the kerogen, and that's where you start getting the hydrogenation effects. But keep in mind that boundary is down at about 400 degrees C in a saline brine situation, and it goes all. So you're dealing with mid to lower crust type environments, which extends the conventional oil window way down into the mid crust where all this stuff's happening. And in the Lewin experiments, the alkanes actually form first in the higher temperature windows.
So it has something to do with where serpentinite is turning into an upper crust rock. Is that more temperature driven, the line between subcritical and supercritical?
Well, no, you can get serpentinites coming all the way to the surface for that matter. But the point is that the hydrothermal, this is the hydrothermal brine product.
It's coming out of this.
That's that's part of the serpentine reaction. And that's the thing that's leading to the quartzes, the talcs.
But the subcritical supercritical boundary is a moving target throughout the crust.
It can be, yeah.
And that's more temperature driven or pressure driven, or we don't know.
It's temperature driven.
It's more temperature driven,
not pressure driven.
It could be deeper or shallower depending on a temperature gradient, essentially. You could
the geotherm. So if you just simplify it and you turn the 400 degrees C into depth, you're looking at around 13 to 15 kilometers there.
Okay.
10 to 15 kilometers.
One step further, entry problem, meaning that as the planet's losing energy naturally through serpentinization, it's making enough from the pressure, water, and temperature. It's making all the hydrocarbon we possibly need.
Well, it's acting like a typical hydrothermal system, which is moving from a high energy source to ultimately a low energy trap, as you like to put it.
And we're not taking this system and putting it back under thousands.
We don't have to find energy to put it back into it. And that's a major problem with the maturation model for oil, is you've got to put it under a basin. You've got to basin burial it to get it up into the oil window. And we have no such problem with that.
Right.
It's just a typical mineral deposit that has some oil in it.
Okay.
And here's another clue to that, which is another anomaly, is that one thing that's not emphasized that these guys want you to pay attention to, which is Petford and McCaffrey, is there's over 400 medium to large oil fields from around the world that are, including serpentine reservoirs in Cuba, for example, in Santa Maria Basin. And White Tiger is a giant billion-barrel plus oil field in Vietnam, hosted in Precambrian granite. Edison is multi-hundred-million giant field northeast of Bakersfield. These aren't trivial. And these are hosted in crystalline rocks beneath the normal basin that people wind up looking at. And their message in this book was, well, you need to be looking down into the basement. And from where we come from, we're looking at this thing from a basement up point of view that is tracking the high energy hydrothermal oil systems.
Right. And through major structural tectonic plate timelines, like the Antler and all these orogenies we have really good timelines on, that's when things are breaking. That's when serpentinization is just ramping and raging its way up to the crust, right? That's those timelines.
Well, you need a big global scale plumbing system, because these are huge hydrothermal systems that initiate in the lower crust.
Right.
Your lovely little cracks of the world story.
The process happens punctuated in geologic time, kind of, with those big tectonic events.
Well, yeah, and one of the things about a hydrothermal system versus a basin burial model is that hydrothermal systems are virtually geologically instantaneous.
Right.
So that whole thing that's going down in that rock there is happening in maybe 100 to 1,000,000 years. And that's been now validated by the rhenium osmium dating.
Right, which we'll get into. But before that,
here's another anomaly. This is the Dimenoid Anomaly. In the early 2000s, there was information published coming out of discoveries that had been made by Chevron, which actually are built on discoveries that the Czechs made in the early 30s when they found adamantane dimenoids that have found effectively diamonds in oil. How do you do that? Because everybody's and their dog thinks that a diamond is a high pressure, high temperature mineral. Now, in terms of how all of this breaks out after all the experimental data, et cetera, we think, and we'll develop this story a lot more later, that dimenoids start forming at about 450 to about 350, and then they get incorporated in every oil. And interestingly enough, when they're in the oils, but they're not in the relic kerogens that's left over. So there seems to be something about when the oil is expelled, the dimenoids seem to go with them. So that's a real interesting thing that we'll deal with later on. Okay, now one of the big things, and this is one of the things that got Troy's attention, is dolomite is a very common reservoir cement mineral or an orthogenic mineral, and you can see how much of it there is here. This is the El Capitan in New Mexico. you have similar huge amounts of this Kicking Horse Rim in Canada, the Dolomite Alps in Italy, on, where huge amounts of calcium, magnesium carbonate are flooded into typically shelf carbonate sections and completely replace them. Where did all of that magnesium come from? And that's one of the things that got us into dolomites in general was they're also form at about 100 degrees C plus or 75 degrees C plus. So it's not you need a warm, wet condition for these things that is above your typical standard pressure temperature window on the surface.
I never really zoomed in on this. And I mean, these features in the cap potential.
Yeah. Those are almost injectite type things that want to take off on you. They're amazing. I mean, there's a lot of mobilization going on.
What do you think the difference between the tan rock and the gray rock is?
Different compositions of dolomite, probably. Calcium magnesium ratios. I don't know.
We'll get up there. We'll collect some rocks, shoot it with laser beams.
There you go. And quartz does the same thing, but these are beauties. These are from Pakistan. They call them diamond quartz, ironically. And here, the one on the left, you can see a complete sequence that is roughly going up the crystallization axis that goes from a platy kerogen on the right side, on the left side, and then it gets globulated, and then it's oil by the time you get to the young growth tip. And you see the same thing here where you got a platy kerogen at where the thing started growing, and then oil at the growth tip.
That thing hits the C-axis and makes a major left turn, huh?
Yeah.
Okay.
But the point here is that typical fluid inks on those things are, like I say, in the 200 degrees C, and we've got a complete sequence here of oil being formed in a hydrothermal context. So there's no question that oil can happen under hydrothermal conditions. Now, a lot of guys will argue with me and say, well, yeah, you made a teaspoon of oil. And I'll say, well, no, there's a lot more oil being made than that. Here's another one, which is magnetite in oil. Now, this is those little black rings in there aren't oil. They're magnetite. And in between, now, which is really wild, is the lighter colored materials there are salt. So Hawkins going to really like this. I don't know if he's seen these things. These are from the Tunguska big iron mine.
Yeah,
it's famous for its. You've all seen what's coming from here, which is the seraphinite clinochlor chlorites. Those are world famous with the lapidary crowd. But not so famous are these things, but they're out there, and these magnetite ooids effectively, and they're giving you a little clue about how ooids in general might be formed as not magnetite spheres, but calcispheres in a hot carbonate injectite vent or mud chamber somewhere, and they are erupted. So all those things that people put sedimentological interpretations on made me want to think those a little bit, not so fast.
Yeah, I got a place in the Permian outcrops next to the Permian Basin that just, this huge stacked up, they call it TP structure. And then at the top, bang, teed off is a bunch of ooids, and it's all, very interesting.
Yeah, I've got a great picture of those that we didn't get in here for the Green River.
So thinking about that, during the time these things were actually being made in a high energy pipe, that's gas release and...
Well, no, that's
liquid fractionation.
Okay, so how do you make the things? You start out with a nucleus, obviously, and then you have a high density brine. So these things then are hitting critical saturation points where a given layer will precipitate out, and then you'll back off on the pressure, or you'll change the compositions of the fluids. But a lot of that's pressure migrating up and down to create these rings. And again, that's saying high energy stuff.
Salt's coming in later. That's the last thing to come.
Well, no, there was salt coming in early. This thing was one salty sucker.
So every ring is what, a plume, an energy change?
Yeah, there's a depositional event around a nucleus, and you can see sometimes that nucleus is a piece of salt, like that little one.
This guy.
Yeah, and the one down below it. And then on the other hand, it's magnetite dominated.
Whoa. So these things are all mixed up. So this one has a similar ride maybe to this one, and then
Yeah.
this one, and this. Wow. Pretty wild.
Okay, this one we're just throwing in here. This is back to the Kupferschiefer again, but one of the things, of course, now in the oil business is that they now recognize that their black shales are not just seals, but they are unconventional oil reservoirs as well.
Right. Seal and source, right? They said seal and source. But now it's seal source.
Self-sourcing, they like to say.
Right. Seal source and reservoir.
Now, the reason we threw this one in is that the Kupferschiefer itself is a shale oil play, as I mentioned earlier. But just below it in the Weislingen is that is the host for some of the largest gas and minor oil deposits in Europe, especially over in the Netherlands, crossing over into Germany. So there's a huge hydrocarbon play immediately underneath it that's associated with the Kupferschiefer timeline, which is better known for its copper deposits. But there is definitely oil and gas going on in that timeline, big time. So here's another thing about black shales is that they generally don't have permeability, but if you heat them up and you hydrolyze them and you turn them into hydrokerogens and you generate oil, you can see how that event itself will make permeability. But it's immediately around the hydrogenation of the kerogen itself.
Yeah.
So it wasn't there, and it was actually probably formed while the black shale itself was being deposited in. So let's go to the next one. Here's another thing that's becoming increasingly famous in oil circles, which is kerogen porosity. And the thing that's interesting about that is the only place you see that porosity is in the kerogen itself. And we look at it from a UDH perspective as a devolatilization texture, sort of like vesicular gas bubbles in a basaltic volcanic flow or in any kind of devesiculation volcanic. So that is actually an volatile exit texture. So it's not porosity that was pre-existing that the oil somehow found. It was made there and lost from the kerogen as the source. That's the better way to interpret it from a UDH perspective. And that resolves that anomaly. Now, the other thing that is increasingly being found when people start looking at the chemistry of their muds is they're finding out that there's a lot of oddball minerals like talc, serpentine, and clinochlor in a lot of these black shale basins. And talc typically is a 300 C plus mineral. How did that get there? Serpentine, similar. It's the same thing with clinochlor. And this is an example from Troy's favorite place, the Permian Basin, where there's a lot of that material in the upper part of the Ochoan.
Right, Castile. This is big anhydrite salt thing that sits on top of this.
Which is also saying, where did the salts come from?
Oh,
because
man,
a lot of that stuff is actually in the salt itself also.
I had a dream.
The talc.
I had a dream about this. I was throwing it out there. I actually had a dream about this when you told me about this, and I was trying to figure out how is this salt anhydrite making itself through the Permian time. It's sitting there, density stratified, floating essentially on this big mud volcanic. I just imagined the whole thing, came up with this awesome model. It was great.
It's bad influences around here. Here's another one, an example from the Louisiana Luan salt diapirs. These guys in 1996, Lock and Do, found serpentine, talcified serpentine xenoliths in the salt diapirs that are going, where did those come from? And they're probably scraped up some of the, what we think is that these are crystallized brine products of serpentinization. So they're not evaporative.
Right.
That's the big message here. You have to rethink your salt geology as from a non-evaporative point of view. Now, when these things do hit the surface, they oversaturate in terms of their saline content and then precipitate out, maybe even evaporate. But the original problem came from the deep, and there's so much of it, you have a real mass balance problem. You have to evaporate multiple oceans. But if you go get it from a serpentine, turns out serpentines contain as much chlorine as any rock in the world in the hydroxyl site. So they're a big source of chlorine.
Right. And so the timing of these diapirs, and specifically then the timing of these world-class reservoirs that pinch up against them, is that a migration story that's pinching it up to the side, or is that actually
that would be he's got sand in there, but if you made that a black shale, what you're doing is that this is an ongoing process. So the brine ultimately penetrates its roof, which was it could have been a black shale at one point that was highly carbonaceous, that was making oil. So all of this is roughly occurring relatively at the same time, but the diapirism can occur quite later. For example, in Europe, the Zechstein salts actually have diappeared up into the Cretaceous sedimentary section. So although their origin is much older.
So if you were to draw this timeline where you have these world-class, let's call them shale reservoirs pinched up against the salt, would the diapir be mostly that stuff, and that the later salt diapir
No, it's just remobilized from the pre-existing Luan salt, but it's coming up as a diapir in the Cretaceous.
Okay. I was thinking that.
In fact, some of those things are even still moving.
Right. Well, yeah, exactly right. So it's all still moving.
That's where our Tabasco salts comes from. Okay, so here's the brine problem, and we're just putting this up here. Okay, that's the Lewin experiment there, and you can see a little oil layer floating on the water that he put in there, which is turned into a brine. That's the brownish stuff underneath it. And he did a little thing where he put salt in the water, and the more salt that he put, the more oil he made. So if you compare where's the oil? Okay, expelled product, yeah. So you can see 3.8 versus about 2.5, 2.7. So he made another percent oil by jacking the
which one were you
salinity up.
I might have followed the wrong one. Well, expelled oil.
Yeah, expelled oil, that's the one. 2.66, and then over, bingo, 3.8.
3.8, yep. Got it.
And I talked to Lewin at a conference in Switzerland, and he said, well, one thing I didn't put in this paper, although I had the data, was about for every percent NaCl equivalent up to about 15 weight percent, he got about another percent expelled oil. So he said, why didn't you put that in the paper? That's really electric. and he said, well, I couldn't figure out why I was doing that. So I just put the first step in.
So we're going to have, Lewin said he'd be willing to come down and talk to us about
well, what we need to do is have a little remembrance session with him.
That'd be awesome. But basically what you're saying is this 5% salt, when the NaCl got involved in the hydroparalysis, when he put this in a lab under a bunch of temperature, a bunch of pressure.
Yeah, it participated in the reaction in the oil generation.
It's making more light oil, mobile oil. And then he took it to 10 and it did even more. Then he took it to 15 and did even more.
Yeah, big time.
And this is a brine.
So here's some brine water that has lithium. And that's just to make the point that there's a lot of people just want to throw this water out. And they should rethink that because there are other elements in there like lithium. The other thing is if you re-inject it back into your reservoir because of that salt issue, you might be able to generate more oil at the PTs back in the oil reservoir. So there's a lot of
especially if you put heat back in the system.
Opportunity that's going on with these brines there. And then you get rid of them as a waste product and then actually you really reuse them to make more oil. That's an intriguing possibility to me.
Yeah. The other, the thing that I keep thinking of is we got to make our frac fluid salty.
Yeah.
Carry this stuff in on something that's a catalyst for this process.
Well, just take the brines and put them back in there with your frac fluids and turn,
Right.
Because what they oil business doesn't realize is that those brines are there as a part of the causal process that led to the oil in the first place. It's not being made from dead dinosaurs. It's being made from reaction of kerogen with hot brines.
Right.
Like it appears to be on Mars. So here we were looking at it on mass with no biosphere around, and it's looking like it wants to make oil on Mars.
Through a similar thing, a Lewis acid, brine.
Yeah. Oh, yeah. And Mars is a very briny planet. It's a chlorine planet.
We get into that later in the semester
Yeah.
or the webinar.
Yeah, we were
series.
anticipating that a couple of days ago.
Okay. Huge masses of brines and salines around the planet.
Again, the mass balance problem here. Where are all those coming from? And again, almost all of those, you can find a serpentine around somewhere. In the basement.
Yep. Oh, that didn't come over. That's on me. You've called out that this one had talc and serpentinite or whatever it had.
Yeah.
You went through.
A lot of those basins have indicators in them of those serpentine minerals, like we were talking about in the Permian Basin.
I'm going to put that page. I'm going to have 2 pages. So when everybody gets this copy of the presentation, this point will have 2 pages. The backup.
Yeah, you need the one that has the actual serpentine indicator minerals in there, or the indications that these things were made as high temperature brines.
Right.
They're not evaporative.
Right. The high temperature mineralogy in there. Yeah. Okay.
Okay, and this just makes the point again. Here we have a high temperature magnetite mineral floating around in a salt bearing breccia pipe. This is a major iron mine in the Tunguska Basin. And here's another example where you've got talc in a diapir in Denmark and northern Germany.
Bering stylolite zone of talc.
Yeah, how did that get into all that salt? And then there's another cool one where they have Herkimer quartzes out of these things that are at about 280 degrees C. And they even say in there that, hey, that means that these things were made at high temperature. So another thing that happens in these is that you get rapid facies changes in the laminated muds that indicate, in many cases, especially if it involves silica, they're trying to say, let's just assume that thing over from the North Sea is a silica thing. All of a sudden you have opal CT next to opal crystalline quartz, et cetera, that indicate changes of 50 to 60 degrees centigrade over millimeters.
Right.
And how do you do that? Well, a lot of people get into the elevator tectonic model for a given lake where they have to go from deep to shallow. And that's really a famous interpretation of the Green River Lakes, for example. And that's Green River right there.
Right. And this
so the black is supposedly forming at depth. And the whiter stuff, a lot of times it's salt. I know that could be a dolomite there. But the point is that whenever they see the salt like trona show up in this stuff, which is right next to it, they go, oh, well, now it was a playa. Well, wait a minute. This guy it had to be deep. So they have a fluctuating profundal model for the Green River Lakes. Mud volcanism model just takes care of that, just sweeps it off the table immediately, because what you've got is just different chemical fractionates that formed on a density driven basis in a mud chamber that just erupted sequentially. So it's just compositional differences. Okay, so that's another thing we'll get into. And then this stuff has come along and started to get out into the literature for oil-related stuff about 2005 for the oil sands up in where they showed that the oil-related bitumens up there, heavy oil-related bitumens, were about 111, as in the Paleontological age for those sediments is identical, and then the black carbonaceous shale lithocaps all fell on the same isocrop for 111. Now, this is doing the same thing with rhenium osmium data sitting around about a 44 million year old isochron. What is it? Was that 43 or 45? Something like that. Oh, 49. So literally all these things form at different rhenium osmium ratios along the isochron that are basically mapping the fractionation process associated with the oil shales.
Wow. The timing on that's just insane.
So the oil itself is down there at the lower end of the thing, and that came from a hydrogenated Kerogen at the upper end of the thing. And so when the oil actually separated, you could see that dashed line there. Well, that's the transfer from and the fractionation event that occurs going from a hydrogenated Kerogen to the oil, and they all basically lay on the same 45 million year isochron. So an instantaneous process.
Right.
And we now have case histories from the Monterey Shale, you name it. I've tabulated about 50 of them. Athabasca was the first case history.
Right. And if I just crossed paths with a guy, he made an observation on a bitumen maturity story with Kerogen from an article, and he goes, I've read this article, and not one thing was mentioned about Athabasca sands. Why didn't you mention anything about that rock? And so
why didn't we?
No. Why didn't the article? The article was making this big burial depth with Kerogen.
Oh, yeah, because the burial depth model there says it happened at about 60. And then one of the problems there is that out where they're at, they don't have any burial that they can do. So what they do is wait a minute, we got a thrust belt over here about 200 kilometers away over there called the Canadian Rockies. So we'll take it over underneath. We'll have some stuff that was over there. We'll make it into these heavy oil sludges, and then we'll migrate them up dip for 200 kilometers over hill and dale and wind them up at 60 million. And then the rhenium osmium came along and blew that whole argument out of the water. So wait a minute, this happened when the Mary Formation was being laid down as a sand, supposed sand, at 111.
Wow.
Same thing going on here in the Green River at 45, 49. Wow. So again, for me, Green River is a complex of mud volcanoes, and here we are over in Azerbaijan at a so-called methane cold seep that is like the old faithful of the Caspian that erupts on schedule every 10 years. And you can see all those little sticks sticking out of it. That's an oil field. It's pulling mud out of and then a bullet train speeding along right next to it, early version of one. But Hawkins been down to this one. He can tell us all about it. And another thing these mud volcanoes do is introduce turbidity to your seismics. And so here's one up in northern Norway that's, look at all that turbidity that's introduced by the mud. It totally scrambles up your whole reflecting packages, makes it highly annoying for the standard seismologist trying to interpret these things. But really what you should look at them is, yeah, there's one on the
this one
west side.
I've seen in the Permian Bay. I've seen this structure. I totally know
except
exactly
that's
where to
over
go.
on the Lopa High in Norway, but northern
The
Norway.
disruption in the turbidity all the way through the Permian and ties into the salts and anhydrites of the Permian Basin. That's there in the data. I've seen it. In the Permian. And also these things that are coming off of this. So it seemed like that's getting punched through. Another one kind of getting, anyway, when you start looking at this stuff.
Well, they're all coming up fracture systems, and they're all going down into the basement. So this process is not just restricted to the basin. It's basement originated. And the oil originates there as well. So now this goes back into the classical experimental oil experiments by Lewin himself, where he created oil at 300 to 360 degrees Celsius. And the important point there is that when he was heating it up, he went through several steps below that, 100, 150, every 50 degree increments. Nothing happened until he got to 300. And then the real action happened between about 340 and 360. And that's when the alkanes come out. And you create that little oil column sitting on the product side of that after sun.
Which is a temperature thing that correlates pretty good to that subcritical, supercritical boundary.
That's correct. Once you just get below 375 is just below the supercritical boundary. So once that thing comes through into the ionic window where you can, that's where you're promoting all these reactions. Then you start reacting with kerogen. It all happens quickly, right as you come out of the window, and then you make your high temperature stuff, which is going to be the alkanes. It's interesting. Here's another fun one from an oil field in northern Norway. That just gets at the idea that this didn't migrate in there. It formed in place like we were doing with that kerogen porosity story. But here what we have is porosity in a dolomite. Those are dolomite class. And then there's a more calcitic dolomite matrix. Well, all the oil that's there is that you see in the fluorescence data is related to those older class that are entrained in what these are basically different phases of a injectite reservoir, which is the host rock. So you did migrate that stuff in there. It formed there, and then before the volcano shut down, which is all of this is probably going down within maybe 1 million years tops. So there was no basin burial going on. This thing happened in place.
And you got turned on to this migration pathway problem or anomaly in a conversation a long time ago. And you talked about how, I don't remember who it was, but you said, we never could find the oil slick. We know the source.
That was a conversation I had with a ex-mobile geologist, and they had a big research on, the classical petroleum system model, source, migration, trap.
Right.
And they said, yeah, we could take care of the source. That's a black shale. Yeah, we could take care of the traps pretty well because we can see them. That's what we're
sands
pulling the oil out of.
Yeah.
But our biggest problem we had was the migration part of it. We never could find something like an oil slick that connected the dots between what we thought was the source, a matured source, and the trap. Now, from where we come from, we said, well, yeah, that's because it didn't make the oil until it got there, number one. And number two, there is a trail, but it's not a oil slick. It's a hydrothermal brine alteration anomaly that you can track all the way down into the lower crust.
Using elemental data.
Yeah. Oh, yeah. Well, you can even see it in the seismic data because it produces, we didn't put them up here, but we have seismic data for the whole crust from Canada, from the Athabasca, that show these big turbidity plumes coming up from layered stuff at the base of the crust, which is obviously a candidate for serpentinite.
And it links right up into these reservoirs that are producing out of.
Yep. And in fact, we even have serpentinites that have come up as dikes that they found in the core just below the Paleozoic section.
Yeah, I've seen that picture.
Yeah.
Amazing. Okay,
They've been talcified.
This one's cool because...
Well, this makes you rethink one of the standard analytical tools that people use to figure out whether they're on the trail of an oil anomaly or not, and that's rock-eval data. And what you do with rock-eval is you take a rock that has some kerogen in it. You don't have to necessarily extract the kerogen. It just burns the kerogen up that's in rock X, although you measure how much you've got. And in the S1 column over there, that you get basically you're looking at devolatilization steps. So S1 typically occurs at about 250 plus or minus 50, and then S2 occurs at 450 plus or minus 50. S3 is the CO2 release, which occurs at 550 to 600 typically. S2 is mainly gas. S1 is petroleum. And the ironic thing in the business is that S2 is typically thought to be the possible produced stuff that you can turn into oil. Well, from a UDH perspective, which is coming from the other direction, S2 is the residual stuff that's left over after the S1 hydrogenated part of the kerogen leaves it and produces that kerogen vesicular texture.
Which is why this has an ascending.
Correct. So we see an increasing, and I've seen this, if you look at a drill hole anywhere where there's good keratin rocky vol data, you'll typically see patterns like this. In fact, you might see them occur over several cycles, but basically you'll see an increase in S1 and S2, but then there'll be a certain horizon where all of a sudden the S1 goes, whoops, see you later. But S2 keeps going on. So what we've decided, the way we interpret this is the S1 is the refractory component, which it was telling us all along, because it doesn't boil off as a gas until 450. That's your oil burning off there into the orange zone.
That's the expulsion.
That's the expulsion, yeah. So that particular horizon in this particular play is a potential shale oil target. Now, they didn't do that. They went after the reservoir underneath it, but there's a whole play up there that might have oil in that particular timeline.
Pretty cool.
So that's a whole nother thing that is hugely anomalous to the conventional oil story. And we'll be talking more about that in the course of the meeting. Now, this is he would call it the Biosphere X, but what this is a hydrogen map. And the main point that Sherwood Lawler and others is making here in the 2014 Nature paper is that in a lot of the deep mines where they were collecting this data, and it's looking for something to play with. And if it finds some kerogen somewhere, it's going to play games with hydrogenating it. This could lead to oil generation in certain places. One of the things that's really cool about that dike that Monty was pointing out earlier that's in the Colorado Front Range, and Hans rubbed my nose into this one since he's there. I'll give him some credit. I'd take the credit if he wasn't there. So he saw all this white bleach stuff, and he says, "Stan, what do you think that is?" And I was trying to go, well, maybe it's clay, maybe it's some bleaching thing. And he says, "What about hydrogen?" And all of a sudden I just hit my head. I said, yeah, of course that's what it is. Hydrogen is a very reactive gas. And so when it sees something like a sand or some matrix component of a rock that it's traveling with, it just bleaches the hell out. It bleaches straight white.
Wow. Now back to the mass balance problem. You come to the conclusion with the previous model that we've grown to learn that oil comes from a biogenic biospheric process. So if hydrogen is pouring out of the crust in all these areas.
Well, serpentinization, which is sitting underneath all of this, is a hydrogen generator. And it's sitting under all the ocean basins. That reaction makes hydrogen. Now, if you're reacting it from a peridotite to a lizardite, that generates a lot of hydrogen. If you're reacting it from a lizardite to a higher temperature, high pressure serpentinite, that also liberates hydrogen. So you can have lots of hydrogen generation associated with that process.
And ultimately, the point is we have so much oil and gas on this planet.
It dwarfs that, yeah.
It's scale correct.
Yeah, exactly. Now, and the other interesting thing is that they're saying all those green things up there, they're saying are Precambrian. Those aren't oil fields.
Right.
And the point is that those basements, everywhere they looked, had a lot of hydrogen floating around.
Right.
Which can leak up into overlying sedimentary basins and play games, but that's
got a lot of oil plays in that. Got a lot of oil play down
well,
here.
That's just
that
you're
follows
getting a
the
little
cracks.
ahead of yourself here.
This one follows the cracks of the world pretty awesomely. That thing,
yeah, you guys.
I kind of got lost on that one, but anyway, we get the point across. Oxidation state. This is something you and Monty put together in the Magma Chem database, right?
Yeah, we like the blue areas for oil.
So blue is reduced crust.
Yeah, that's a hydrogen-rich crust.
And
the red is an oxidized crust.
Got it.
And oxygen is the enemy of oil formation. If you hit an oxidized zone, it's game over.
So that's San Juan. That's
and
permanent.
what it'll do ultimately on a geologic scale is oxidize any reduced HC to carbon dioxide, CO2. So you don't want to be in that. We'd modify that a little bit, but that's one reason why there isn't a lot of oil in Arizona, for example, is that the magmas that came up through Arizona crust oxidized and made copper deposits.
The whole you go into this, which everybody has access to, the detailed Cracks of the World 2003 publication. You go into a concept of why the oxidation state of the crust would have a funky pattern, but more so why every intrusion through geologic time in a given area generally, maybe even more than generally, stays the same oxidation through geologic time. So there's something going on with oxidation.
Well, that's
state.
a mass thing. So the more mass you equilibrate with a certain oxidation state, the harder it is to reverse it. And typically these things want to get more and more oxidized with time. Because once you do oxidize it, it's hard to reverse it back into make it reduced again. Although you can, if you have enough hydrogen flux, you can reverse that.
And apologies for not having a good description of this map. Sorry, Monty, you want to say something?
Yeah, if you put a big arc, like a Jurassic arc in, you can oxidize it. But that oxidation state pattern is following old terrains that have been accreted together into the continent. So like in north central Nevada, that's a oceanic terrain that's stuck in there. So it has a low oxidation state. And, you know, the gold and the oil and the diamond
follows that reduced blue area.
follows reduced. So this is basically contouring the commodities, and they follow the big structures, as you can see there. That's a basement structure map I constructed from all sources, and just to see if we could outline these oxidation state terrains.
So
and it does beautifully.
Monty, can you explain just real quick, because we don't have a description on this, and I apologize for not having a description or a north arrow. I was taught better than that, but we got it in here. This is so. Explain all the features real quick on this map, Monty.
Well, we have the fracture zones out in the ocean.
Discussion.
And the fracture zones, the oceanic fracture zones, basically define different buoyancies of crust because there's different ages of crust. So when you subduct those, you tear the subducting slab. So those lines, those northeast trending dash lines, are tears in the ocean crust as has been subducted. And so that forms major tectonic geologic provinces. The panel of crust above those panels are their own geologic province.
This is is this the backside of the Farallon plate right here?
That's the ultimate paleo-subduction zone. It is a topographic feature out there, but
there's
and
a
then
lot.
Oil
it's not there anymore because you now have the transform. Things turned into a transform margin.
All right, and then we got oil and gas in outlined here, the polygons, and then oxidation. Okay. Sorry for that non-description and a little bit jargon. Okay, here is the last of them today, and that we are going to dive into in gory detail, as Stan says, every Thursday, the same way. As you get feedback, we can switch it up and change things and make it better, but this is how it starts. This is the last one. Then we're going to get into the whole UDH model, explaining this integrated model that takes mantle to crust, ultimately to everything we see on the surface. So here's the last one going into the end.
So if you bother to read the fine print up here, which I'll just sort of summarize for you, but you can read it at your leisure later on. Basically, the chemical problem with converting kerogen into oil is you start out with something that is the chemistry of kerogen, even a relatively hydrogenated kerogen, is HC. More typically, it's H.5C. And you got to take that up. Bulk oil is H2C, ironically.
Hydrogen deficiency in this process. Hey, Monty, can we mute your microphone?
Well, the bottom line is you have to find hydrogen to get from HC to H2C. Now, you can do that by cannibalizing the HC to H2C, but you run out of HC in a hurry doing that. So the more convenient way to do it is to use H2O and get the hydrogen from a water donor. Wait a minute.
Oh.
And that's what Lewin was doing. So 2 moles of HC are required to make 1 mole of H2C. In the presence of water, you have the H there. In fact, if you add that to it, you even have hydrogen left over. So there's plenty of, that's where you go for your hydrogen. And it's a hydrogen unlimited process, whereas the other way, just by simply heating it and cannibalizing it to make H2C, that you limit yourself in a hurry on a mass balance basis. Where if you're using hot water, no problem. You've got endless hydrogen.
Which this next page is one of the final things we had in our Dimenoid production that we spent a lot of time on, that we'll get to it around week 3 or 4 or something like that. But this is basically you taking a Lewis acid, brine from the oceans.
Well, I'm using a hydrogenation process here that involves some of the minerals. In this case, what we're using is muscovite. So we have a muscovite illite oil factory up there. And the idea is you're crystallizing illite, you're reacting it with, or mostly it's muscovite because you're above the 200 degrees C window. So you're taking an H2O plus an 3HC brine plus bromine. And that's really important because that chloride makes halogenide makes a Lewis bromic acid, and that creates what we're not talking about here is the dimenoid story, which we show down there at the lower left. And the dimenoids are real important, and we'll get into this in detail in the course, where the dimenoids act as molecular platforms on which to polymerize alkane chains. And then after they get really hydrogenated, they break off into liquid oil. And all of that process is happening during the crystallization, solidification of the muscovite in this case.
Right. Building muscovite clays, phyllosilicates, in a brine solution, and it's in that process.
You need that brine there. I mean, that's a necessary part of the process.
And just muscovite illite promotes oil generation better than the other types of phyllosilicates. This is the best one to make
because
oil.
they provide their own platforms as phyllosilicate planar faces on which you can have all the appropriate electrostatics that you need to accompany the polymerization effects.
That's right. That's right. Okay. Now you're cleaving off at the end of this process. You're making bulk oil. You're cleaving off the dimenoids. It's going with the oil.
Exactly.
And we're left with the rock that was left over. The brine, all that stuff moves on, moves out.
Well,
could move on,
no,
but it moves out.
Some of it can, but some of it stays behind.
Right.
And you have the oil plus brine relic, and there's your another example of vesiculated kerogen. And note that the porosity in that rock is right where the kerogen is. You don't see a lot of porosity anywhere else.
Right. It's that expulsion.
Yeah, and in some reservoirs, what happens is that in that area where it's actually gone to oil, is it the entire kerogen has been reacted into oil. And so you'll have a cast left behind that was kerogen is now completely filled by oil. And this oil reservoir up in Norway has a lot of that going on.
Wow.
And that happens in the context of an reacted injectite.
Right. So we go through this incredible list that Stan and MagmaChem has put together over many years of studying this planet and seeing these anomalies in the data reoccurring. We put them all together to give an idea of how we're going to get through this semester or this webinar series of how really the UDH model that is finally being taught for the first time publicly through MagmaChem Research Institute, it provides a potential solution to all this stuff. It's not an anomaly that you shelf anymore. Bring them back in, apply a model that can accept those, and in your experience, you've seen time and time again, the model not only uses them, but it's actually key information to make the right prediction.
specific and it's predictive. And if you take all those anomalies we just went through, if you're intellectually honest, you're going to have a hard time believing in the original conventional oil model that's out there that you learned in the textbooks. You're going to have to start thinking about another way to look at things. And as we went along, we were looking for that alternative explanation. So we wind up building it as we solved each anomaly in detail.
So it opens up the scale, and that's the biggest thing about where we're going with this whole presentation. Not only can we use all of these, wild things that we see in geologic rock record to try to help us find something of economic value, we can use it now, but you got to open up your scale. You can't just be basin focused, and you certainly can't just be postage stamp where your acreage is focused. For you to really understand that the mantle and the crust is fully integrated from rock to rock process, the full process. You got to open
Well,
up
that little inset there, go over to your right. Yeah. No, stop right in there. You look at that thing, that whole thing needs to be regarded as a petroleum system, because if you do the classic model, the source is down here in these peridotite layers, and then they get mobilized through various tectonics. And then once they cross the supercritical boundary, which we've got in that little dashed line up there, that's where you get the reactions to turn it into oil, and then bingo. You get typical basin traps, but you got to be looking out in those crystalline rocks, because they can have oil in them too, depending on what the local geology is.
Well, at the end of the day, we're trying to find in this little reservoir in the basin, where is the biggest bang for my time and attention, or my buck? You got to know where that system's coming from in order to have the highest possible resource you could find, the biggest and best.
Simple answer that the Russians have known for years, decades. It's known as the Korczynski Role. And basically they say that in their observations of oil reservoirs, they tend to be stacked. And the deeper you go, the more alkane it gets and the bigger it gets. So we've only been exploring the tops of these systems.
Wow.
The deep play is out there just about everywhere. That's why LA Basin is going to be pumping oil until we get sick of it, because it's below the basin down in the Orcopia schist. It's hosted in that mainly.
What the hell?
And where did that come from? You can't get that from the Monterey source rock. It's sitting way the hell thousands of feet above that.
Right.
And in itself is hosting oil. So how do they do that?
So another epiphany for me anyway was, okay, what is the UDH webinar series amongst all these things that you've done in MagmaChem and how everybody understands it that's really intimately close to MagmaChem? What is different about this class or this webinar series? And Stan, you said it was you've integrated the Serpentosphere into this model you've been working with.
Well, Serpentosphere is your soft rock geology.
Well,
and related processes and mineral deposits like porphyry coppers, like we have around here in Tucson, is the hard rock side of it.
Right. So the UDH process is truly the integrated process between mantle and crust.
Well, yeah, because it's making these high density brines, which are the source of all this mud volcanism.
Hey,
so
Troy,
that's soft rock.
Right. Monty?
One thing to say is that you also get metal deposits from serpentinization. It's not just oil. And I'm kind of thinking you've got hard rock, which is peridotites, which is a precursor to serpentinites. Serpentinite is kind of halfway between a soft rock and a hard rock. It's a step between the two, because it's not a peridotite and it's not really a sedimentary rock. It's a hydrothermalite. It's fourth rock type.
Well, yeah, this kind of gets at what Monty's saying right here.
Right.
But there's major metal deposits related to serpentinites. In fact, a lot of like Mississippi Valley types.
Right.
The Central African copper oxide deposits. I mean, those are major things. And maybe homestake. Homestake might be serpentinized, magnesium-rich peridotites.
Okay, let's talk about this process of dehydrating the peridotite penisphere to brine expulsion and making rock in the crust. I mean, this is a little bit higher resolution of this transition that's happening between the subcritical supercritical boundary. It's happening in between the mantle layer and the layered earth model.
One of the major processes that you have to think about here is, what does a UDH system? We've been focusing on what it looks like once it gets up into the overlying so-called sedimentary basins. But one of the things that we marched around in Norway on with Hans, if he's still out there, and we rubbed our noses in what was potentially going on with the UDH system in the middle and lower crust. And one thing we stumbled into, in fact, Hans grew up in a world-class talc deposit called Altamark. And basically that's a product of steatization of serpentinite, which is literally going on right within the deposit. And when that happens, that dehydration reaction creates a hell of a lot of brine water, which can make dolomites, and it can make these things that we now are calling UDH complexes. And they've always been sort of funny metamorphic things because they're just floating around in the basins, and they're just sort of, they cross-cut it, and nobody's really ever related them to what's going on with the metamorphic basement as their own event. So when in fact they're the UDH story coming up through the crust. And we plotted UDH complexes in Norway, and they have sort of an amoeboid spatial distribution that looks very similar to the oil fields and the overlying offshore fields that are up in the North Sea and Norwegian seas.
That's an interesting structural correlation.
Well, it's a geographic correlation.
Okay. Okay. So we need to end it in order to have discussion. For everybody that's still here, we're going to open it up to discussion, and just as long as you want to stay, we have a meeting at 1, so I guess we'll go at least till 12:30-ish on a discussion. But the course for me is taking geologic processes, geologic concepts from universal scale, what's happening out at Mars and anywhere else in the universe. It brings it into our planet's history, and then we go from the mantle through this transition into the UDH system that allows us to find these resources that we have on this planet. It also has a lot to do with the story of life. It has a lot to do with everything. It's a fully integrated model for us to understand the natural processes of a rock in a solar system. And we're gonna go through the whole freaking thing just like this, time and time again, just diving into the details in hopes that we inspire someone to ask us questions, which we have some chat.
Anybody out here? Anybody out there?
So that's the end. Yeah, there it is. I'm going to get rid of this real quick. That's the end of the official week 1. Hans has raised his hand, and
I knew he would want to talk.
Let's go into Q&A. Thanks for the presentation. You were talking about kerogen, part of shale rocks. Do you know the effect of the absorption in the production from shale? This is Georges from U of North Dakota. Thanks for your answer. Yeah.
Let's let him talk a little. I need to get some clarification on the question.
Okay. So,
is he out there?
Hey.
Oh, here's somebody.
Hello.
Hello, sir.
Thank you so much for your presentation. It was so amazing. I think that it's just a couple of minutes for you. Thanks. Yeah, my question is related to my research is related to corrosion and kind of porosities in shell, and you explain the effect of the corrosion. But it's not, we try to find more about the absorption, the effect of the absorption in the corrosion, how the gas, the methane is sticked in the corrosion, and how the effect of this in the production for our research, our formations, you know. The Bakken has that problem. We are working in Bakken. Yeah, thanks for
Bakken.
Yeah, okay. So, yeah, that's sort of the classical using the kerogen as a sorber, using the porosity to stick stuff in. What we're saying is that the kerogen porosity is an exit texture.
Mm-hmm.
It's losing its volatiles. So it's the opposite. It's not about sorption, it's about desorption.
So what about when we depressurize and we bring things on production? What is the kerogen doing to the hydrocarbons around it? Is it allowing it to release, or is it holding on to?
Well,
them?
no. Okay, so let me go into that a little bit more. So if you have a lot of rock eval data, what you'll find if you do kerogen S1 and S2 maps and S1, S2 ratios, et cetera, you'll find that the areas of high S1 are going to be where your oil is, because that's the free oil. And what's interesting about what the other argument was doing was that they were looking for high S2 because they wanted to say that was potentially productive. From our point of view, we're looking at where the S1 is, which has been produced, where it's been pulled out of the kerogen. Now, if it migrates somewhere, if it finds a fracture or something to migrate on, then it might leave. But a lot of it is actually in situ.
So when someone says absorption,
it formed right there. It didn't migrate. So the idea that it migrated in there may be you may need to rethink that.
Interesting.
It formed right there. And then it may or may not have migrated from a UDH perspective.
Sir, thank you so much for your question, man.
Does that make sense to you?
He went back.
Yeah.
Oh, here we
Yeah.
go.
Okay.
Yeah, great. Thank you so much.
That he's going to say, I don't believe in it.
No, yeah, it's great. Thank you so much.
Cool.
Yeah.
You need to think about it.
All right, let's go. Hand raise number 1. Here's Hans.
Oh, Hans, you can't shut him up.
Uh-oh. All right, is Hans in? He's got to turn on.
Well, I don't know who this is.
Can you hear me?
Question is this?
Yeah, we can. Is this Hans?
Yes, this is me.
Hi, Hans.
I was not sure whether you could hear me or not, but I've been following the whole thing, and it was great to be back, so to speak.
Yeah, it is. It's great to talk to you again.
Yeah,
of course, last time we talked was over in Scotland. So.
Yeah, that's right. No, I don't really have a question. I just want to congratulate you with your presentation. It was great, and
Wow,
I will probably think of some.
Oh, I know you will. And you're free to communicate it at your leisure.
I will think of some almost intelligent things to ask you, but not at present. I just wanted to congratulate you with your presentation.
Wow,
Okay, thank you.
I thought it was that one. Okay, so what is Don's comment here, Stan?
They're comparing it with the Shell Invictus thing in Africa. And they're saying that some of the seismic sections that we put up there remind him of that. But my question back to him is, what did Shell ever do about all of the opacity that was in the seismics? Did they try to process it out, or did they say, oh, maybe there's fluids in that opacity? Tell Molly we have some cool strike slip faults to show her that we came up on from Mars.
I'm going to make that an animation and put it out on.
Yeah, we need to put that out there as a follow-up.
Oh, yeah.
She'll love it. Strike
slip on Mars is amazing. All right, Monty, anything
I've got one from Gary Heinemeyer.
Is that right?
What?
Gary
Was he
Heinemeyer.
listening to this?
Yeah, oh yeah. So he says, I have been enjoying watching your webinar and it's very well done. All of the black breccias and layered black micropyroclastics I have noted for years in working on gold deposits must have kerogen per your web presentation. I even have pictures of feeders for these from Rawhide and White River. Pretty neat.
You guys would agree? Kerogen should
Yeah,
be
I
there?
have no problem with that. There's a lot of kerogenous veining in Carlin type deposits in particular. And in fact, in a number of them, Yankee being a notable example, there's actually hydrocarbon seeps where there was enough hydrogen around to get to the oil window, a hydrothermal oil window.
Dan Laux has showed up. There's Ron Luthi. Scott.
There he is, fly on the wall.
Sophia. Oh man, that's awesome to see you guys on the list. Dan, let's see. I'm going to promote you, see what you do. You don't have to turn on your mic or anything. But
Well, Dan can tell us a little bit about the early Magma Chem days.
right.
He's got
We
some
did make
stories, if nothing else.
right. Did make us an introduction. I don't know if you saw that or not. There's
Oh
Dan.
my God, there he
There,
is.
I have to agree with everyone else that I'm amazed that you guys did this so well. And
Thank you, Dan.
yeah, I would have to give Troy all the credit for
What do you think about
directing
this,
the
Dan?
stand.
That's right.
Well, he
definitely
tries to
kept
ride
Stan
hard on
reined
me.
in. Yeah.
As you saw, I resisted him several times.
Dan, so
No.
take us through a little bit of your perspective on this. When you showed up with Stan, how did you cross paths with Magma Chem? You're obviously highly regarded by everybody. I mean, Dan, you've been such an important part of this story. How did that all happen?
Well, I had a summer job at Carlin Gold, and I wanted a full-time job there, but I was
That's
too
right.
green, I guess, and so I didn't get one, and they would have had me ridge and spur soil sampling until the snow flew, but I decided, screw that, I'm going to go audit classes at ASU and get into grad school. So I take Western Regional Geology, and
man.
3/4 of the class is working for Magma Chem.
The glory days.
They were hand plotting all the petchem data by hand, I'm
Pre-computers.
sure. Yeah, pre-computers. So in any case, I came on board, and I was one of the lucky ones because I didn't have to hand plot petchem data. I got to draft all the Exxon time slice maps.
Wow.
And from there, I got into compiling mineral district information because Stan also had quick and dirty mineral district maps for all the Western states.
Wow.
And so I just fit
That's
right
part
in.
of the Exxon compilation.
Right.
Wow. We got Don. He says another word here. And, sir, you can definitely come on, but he's saying new geological and geophysical work. He de-risked the acreage. Ingredients for working petroleum system present in the basin, source, reservoir, and seal, all present and sampled at outcrop, Western SG 4571, and mapped into subsurface, lower Triassic source rock.
Oh, okay. So now we're back in Africa. That's the Karoo. Oh, wait a minute. There's Kaborka.
Mm-hmm. We are going to constantly try to stay within 2 hours, really in an hour and a half, because the discussions is obviously where it really gets good. But we pretty much took 2 hours on this introduction.
So one thing Gary asked is, will this be archived on the website so he can look at it,
That's right.
slowly?
Yeah.
He says there's so much here, he's got to go back and review. So
Especially if he gives us a few dollars.
All donations totally welcome.
We'll go cheap.
So yeah, we're obviously
get that time slice that map off of there. We need another cover illustration.
okay. We'll mess with that. So the Magma Chem Research Institute is obviously built by the community that we're building. I mean, this is all we got. We're doing everything we have to continue to do these presentations. So we wanted everyone to focus on the Magma Metal Series approach and really understand the mantle side of this. So that's the first publication that you can get access to, along with major other available publications that are free to you after you become a member. They have a lot of information too. So this is definitely where you want to begin in order for us to get the most value out of these courses. It sets you up for that. And so now when you go into Introduction and Anomalies, you'll understand what it was, and then there'll be a video that you have available to you and forever that you can watch this conversation, and you'll have every slide that we created for this presentation. So that's what you're getting in these courses.
Will they get the audio too?
Oh yeah, audio, video. And next week we're going to the geology of Kerogen. We're going from how is Kerogen universal, how that discoveries from Mars and everything else that's happened on meteorites, how does that play now into the layered mantle? the dynamic earth model that MagmaChem has, and how do you bring it up to the surface? That's where we're going with geology of kerogen. The next one, as Stan has somewhat approved, serpentinization and steatization. This is kind of that transition area, getting into the subcritical, supercritical boundary. Hydrogenating kerogen. You're going from primordial, low kerogen TOC quantity, but incredible volume, scale size volume. You hydrogenate that through serpentinization and steatization, and now you get the kerogen that's ready to make oil.
And you get more of it.
And then we get into
Hydrokerogen.
supercritical, subcritical, how dimenoids are absolutely important. And when you run the analysis you need, which MagmaChem has done for many years on dimenoids, it fits into your story. It totally helps you find where that high productive zone is for oil generation. And then we'll just go down the list. And so every time you come in, you get access to what we just did. So if you miss it, it's here. You can come back, and for a minimum donation, you can get access to all of this stuff. But if you're in it and you say, can I just see it again? Yeah, you can. Of course you can. Let's do it again, and let's integrate some ideas. But at the end of the day, we're a nonprofit that's trying to put something out there of value that is a resource, and it's worth your time and certainly worth your money. So that's the goal with getting through this mud volcanism, injectite, and then this one at the end is the application of this through the Gouda case history that you guys did in Norway, and these final maps and this final presentation is it. I think it's a guide to help anyone de-risk their investment of their time and attention on a resource play.
Sure.
That's our goal with this. And thank you guys so much for joining. And if anybody has anything, last words, we'd appreciate, or we'll call it good. Monty, any final words?
Final word is thank you, Stan, for being so articulate and a just great stream of consciousness through the whole. I really appreciate it. And Troy, you're the glue that's holding this all together. I want to say the fragile thread is not a fragile thread. It's a pretty strong cord that's holding this. So thank you so much.
Thank you, Monty. Thank you. All right. We'll see you guys next week.